Starting the presentation, I'll go with a brief introduction of Blue Wave AI. It's a privately funded company in Canada, founded in 2017. It's on the intersection of smart grids and artificial intelligence, leveraging IoT data and cloud computation. It's a software as a service company and has so far multiple deployments at different utilities, renewable energy operators, independent power producers, and an IP portfolio of 10 USPTO patents. In terms of our customers and partners ecosystem, we have projects and deployments partners on 3 continents. On the utility microgrid sides, we are working with Tata Power Mumbai, ABB, Green Cat Renewables, Hydro Ottawa in our own backyard, Ontario Independent System Operator, IESO, obviously Summerside Electric, which I'm going to talk about today, Georgia Power, and Tuglik Energy. We have a wide range of EV fleet operator partners and customers, as well as other type of academic and industrial partners, as you see on screen. Our product is hosted in the cloud. Our platform is a distributed AI platform consisted of Blue Wave AI Center and a Blue Wave AI Edge. The center is hosted in the cloud. The edge can be logically hosted in the cloud or physically reside on the customer's premise, and it interfaces with the customer's assets, components, controllers, so on and so forth. Obviously, the Blue Wave AI Center also interface with the end user customer configuration centers and also external data sources such as weather service providers, traffic system providers, so on and so forth. And the philosophy of the company is to provide a holistic end-to-end solution that combines predictive analytics. It combines data-driven adaptive optimizers, as well as the distributed energy IoT platform. And at the end of the day, deploying data-driven techniques that brings more revenue to the customer's operation, reduces the supplied cost of energy, reduces emissions, and increase the electric miles driven by electric fleet operation systems. We have received a wide range of awards and recognitions throughout the life of the company, including being the Smart Category winner at the World Energy Council in Abu Dhabi in 2019. So with that brief introduction, I'm going to dive deep into the example that I'm going to discuss today. It's an optimal energy scheduling system for the city of Summerside, for the utility of Summerside Electric. The utility, basically, the city is a relatively small city. It has a peak load of 28 megawatt. But the interesting thing about the utility is its high wind penetration, 12 megawatt of wind penetration coming from 4 different set of 3 megawatt turbines. There is on-site diesel generation systems as well, multiple diesel engines for a total of 15 megawatt of generation capacity. And basically, the city has on-site solar farm. It has on-site battery energy storage systems, and it's expanding the solar farm and battery energy storage system as we speak. I'm not going to focus on those areas of this system for my talk today, but the type of projects we have with the city of Summerside is quite extensive. We have an optimal battery energy management system, a wide range of different prediction systems, so on and so forth. But for the sake of study, I'm just going to focus on a particular problem in the city, which is about essentially scheduling the energy from the upper grid in view of a prediction of the wind energy generation, in view of the prediction of electric demand, in view of the prediction of the solar farm, which is getting expanded. Again, I'm not going to discuss about it today. So they have to schedule their energy from the upper transmission level system, which is the NB Power, New Brunswick Power. The problem is that any inaccuracy in that schedule will be penalized by the NB Power. And as a result, there is a need for a system that would be able to account for all the predictions coming from different generation resources, consumptions, and schedule an optimal mix of generation from the generators on site, as well as the energy that is going to be scheduled ahead of time from the New Brunswick Power. So this product that I'm discussing today is an optimal energy scheduling or a predictive scheduling system that is currently deployed at the city of Summerside, has been in operation for the past 2.5 years, 24/7. And just a very rough schematics of how does it work. There's a Blue Wave AI Edge with its own prediction systems and predictive scheduling system, which is interfaced again through the cloud with the Blue Wave AI Center, which includes all the crucial elements of the project, such as database. The training happens, the artificial intelligence training happens in the center. All the analytics, the updates to the products, algorithms, so on and so forth. All of those happens in Blue Wave AI Center. So as I mentioned, there is a high penetration of wind energy in this utility. For in terms of their energy mix, basically their annual energy consumption sits roughly at 275 terawatt hours, out of which almost 25% is coming from wind energy alone, and the rest is coming from the upper grid import. Soon this figure would go under a comprehensive change with an introduction of close to 20 megawatt of solar farm, which is very significant solar farm size compared to the size of the city. But at the moment, dominantly driven by wind and by the import from the upper grid. There's a little bit of diesel generation going on, but we completely displaced that diesel generation. Previously, it was running because of some inaccuracies in the optimal energy scheduling. Also, for the maintenance of the diesel gensets, you need to run them every once in a while. But at the moment, the diesel generation, you can kind of comfortably ignore it. It's only sitting at close to 0.2% of the total generation of the system. This is just basically the actual wind generation, I believe, for the year of 2019, if I'm not wrong. Hourly generation measurements. There's obviously the x-axis here is the number of hours per year, and then this is an actual yearly annual profile of the wind turbine. So the blue color is hourly measurements, as you see, quite fluctuating. There is a cap of 12 megawatt coming from 43 megawatt turbine. The black line is obviously the wind turbine generation duration curve. For example, it means that obviously for almost for example, if you find for 10 megawatt close to 1,000 hour of the year, the generation has been higher than 10 megawatt. Close to 3,000 hours of the year, the generation has been higher than 4 megawatts, so on and so forth. So a relatively normal pattern and output of wind energy coming from the 12 megawatt wind turbine. An example of a month coming from a single turbine is also shown on this slide. Again, you can see comfortably all the fluctuations happening in the turbine. This is just an example and a snippet of the turbine generation in 2017. Obviously, more recent generation would be similar. The point of this slide is just to show you the highly fluctuating operation paradigm of each individual single turbines, which is 3 megawatt, 3 megawatt turbine existing at the utility. So just to go a little bit deeper into each one of these generation profiles, we can have a look at the profile decompositions to understand how much of the profile is seasonal, how much of the profile is random, what is the trend of profile, so on and so forth. So the profile shown on this slide is decomposed into 3 different signals that can be added together to essentially construct the profile on this slide that comes from a single turbine. You can see that there is not much of a strong cyclical pattern. The seasonal pattern of the turbine is peak to peak close to 600 kilowatt, but it's dominantly driven basically by random fluctuations of of the turbine and the random pattern of the wind speed, wind gust, so on and so forth. So the idea here, the focus of this presentation is on one of the elements of this optimal energy scheduling system, which is the wind prediction system, right? So to be able to develop that wind prediction system, we use 3 different data sets obtained from the Summerside Electric, as well as some of our own external databases related to weather signals. These data sets combined provided us with essentially 123 different signals that was eventually used in our prediction system to develop a energy forecasting for the city of Summerside wind farms. So that energy forecasting system itself has multiple steps. Some of these steps are routine. Some of these steps are kind of the secret sauce for Blue Wave AI. Most of the secret sauce happens here in the predictor model itself, which we use an ensemble of various machine learning different techniques to be able to predict the output of the wind turbine. Some of them is less secret sauce, is more routine. Obviously, you're going to have a database, which is for us is hosted on the cloud on Microsoft Azure. We have developed a standardized data processing techniques to process the raw data, make sure it is of high quality and it is the quality to be able to ingest it by the entire prediction process. Out of that, you have to extract the signals that are relevant to your prediction. Again, we at the end of the day, we end up looking into 123 different signals, perform various type of statistical tests to make sure that you extract all the predictive value available in the signals to, at the end of the day, to develop a prediction system. And this is an iterative process. You have to go through an iterations of feature selections, signal selections, model tuning, so on and so forth, so to eventually arrive at a prediction system that is suitable for the operation. We have a wide range of energy forecasting system developed. So most of these blocks that you see on the screen is kind of in a plug and play mode at Blue Wave AI in using our standardized data factory system, using our standardized data interfacing system, processing system, so on and so forth. And we have a wide range of forecasting system deployed and in operation in various utilities throughout the planet. That include Tata Power Mumbai, again, city of Summerside, Green Cat Renewables in UK, Georgia Power, so on and so forth. I'm not gonna reveal the details of the performance due to the confidentiality of the situation. But what happened is, since we deployed our product at the city of Summerside in 2019, for over 2.5 years, the product has been in operation 24/7 with no interruption, and has managed to reduce the operational penalties of the system as compared to the legacy system by a factor of 2. So in other words, this blue and gray color are actual savings we brought to the system, is just normalized to the system operation costs. And as you see with the legacy systems, the savings that you can bring from reducing the penalties has been just half of the savings that we brought by our product. Basically what it means is that we decreased the supplied cost of energy for the city of Summerside through decreasing the operational penalties of the system, or in other words, bringing revenue for the system as compared to their legacy system. So far, for the past basically 2 years, there has been an average of 47% wind power penetration on the power side of the story. And so if you look at the power output of the generators, so this is just a snippet of our actual product dashboard, which the system operator is currently working with. This dashboard helps the operator to monitor the system operation throughout the operation at a custom range. Currently, you're looking at the past 15 days. I actually take a snippet of this yesterday, so you see basically it's up to date. It belongs, the last day on this is 27th of October, and it shows the past 15 day of operation in the system. Various components exist here. This is the wind predictor, right? So we have a PV predictor, we have a load predictor, we have the optimal energy scheduling system, we are taking control of their battery. But the component that I have discussed today is this component, the wind prediction system. Basically, the green color is the actual wind power output coming from the wind farm over the past 15 days. As you can see, it's been very fluctuating, often on the lower side of the generation, but for the past day was generating close to maximum capacity. So the green color is the actual generation of the turbine, and the blue color on top of it is what we predicted is going to be the output of the turbine. So as you see, quite an accurate prediction system is developed and implemented for the city of Summerside when it comes to their wind turbines. Again, this is combined by a wide range of other predictors and optimizers on the operation of the system to brings eventually savings and carbon savings as well. What you can see is we actually saved the system to 949 tons of CO2 over the past 15 days by displacing their diesel gensets, as well as enabling a full consumption of wind energy without putting it back to the upper grade. That brings an end to my presentation for today. Acknowledgement is for this Summerside Electric staff. In particular, it's two of its director employees, Mr. Greg Godet and Mr. Joel Giro, which has been exceptionally helpful and accommodating for working with Blue Wave AI throughout this project.